Hello, Math 201. Welcome to today's lecture, graphing functions. And so this is kind of an interesting section because a lot of you are probably familiar with how to graph functions and the basics of graphing functions. And the idea of this section is we're going to use all the stuff from 4.3 about what the derivative tells us. And we're going to use all that information to aid us in graphing functions, all the stuff about increasing, decreasing, concave up, concave down. All that stuff will help us to understand better how to graph a function. And one of the reasons why this is important, because you might ask, like, why do we need to know this? So it's important to know what graphs look like so that you don't just blindly follow a computer, right? If a computer generates a graph, you need to be able to know whether or not that it coded it correctly. And so just understanding basics about how functions work is a really valuable tool in being able to understand that graphs are doing generally what you'd expect them to do. And the idea is we're going to follow these guidelines. I'm not going to read all of them because you'll have it, but I'll basically talk about the ideas. So the first thing you do is identify the domain or the interval of interest. So we want to know what X values do we actually care about. So the important thing here is to remember that square roots, right? If you have square roots, they have to be positive. And if you're dividing by something, it can't be zero, right? You can't have zero on the bottom. We want to exploit symmetry whenever, and this one's not super important either, but we'll talk about that. Remember, even functions are they're symmetric across the y-axis, and odd functions are symmetric along the line y equals x. And so you can use that advantage. This is the real crux of what we're going to do here, 3, 4, and 5. And the idea is this, is we're going to make a number line for f prime and f double prime. And that number line for f prime and f double prime will really give us all the information we need. It will tell us when it's increasing, decreasing, and it'll tell us when it's concave up and concave down. The other things are not as important, but identifying extreme values and inflection points. So that's using the first and second derivative tests, locating asymptotes and determining end behavior. That's taking limits, but again, we won't talk too much about that. It's really 3, 4. Oh, excuse me. It's really 3, 4, and 5 that are going to be the main things. And then finding intercepts, that's old kind of stuff. And then appropriate graphing window, so knowing what values make sense. So once you have extreme values, generally plugging in values to know what values. So let's do an example. So here's a warm-up problem. So I pre-drew a number line for f prime, an f number line for f double prime, and I want the x values to match. So 0, 1, 2, 3, and 4. And I drew dotted lines to kind of give an idea. And then I'm gonna use the information from f prime and f double prime to give a sketch of what a possible f will look like. And so what does it say? So f prime is negative on negative infinity to 0. So negative. So the value here is negative. And f double prime is positive. So positive. So what does negative mean? It means it's going down. And what does positive means? It means concave up. And so I draw a little picture like that. On the next interval, 0, 1, the first derivative is positive, the second derivative is positive. So it's positive, 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 positive. So concave up and going up. So this right here from the first derivative test tells us that must be a local minimum there. And it's also concave up, which makes sense. The next interval on 1, 2, this one is positive. And now the concavity is negative. So still positive, and now it's concave down. And so we switched concavity. So this must be kind of an inflection point, right? It's probably going to look something like that. And then on 2, 3, they are both negative. So negative, 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 negative. It's concave down, downward slope. And so concave down here, and it goes from positive to negative. So it must be a local max. And then f prime is negative here, but positive here. So it's down and concave up. And then finally, it's positive, 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 positive. And so it's going to be increasing and concave up. So now putting all this together, we can sketch a possible graph that's continuous. So the idea is that it's going to go down and be concave up. And then it hits a point right here at x equals 0. And it's still concave up, but now it's increasing. And so that's a relative or local min. And now it's increasing, increasing. And then at this point, x equals 1, it's still increasing, but now it's concave down. And so this is an inflection point. So it inflects, and then it will start at x equals 2. It's still concave down, but now it starts going down in the negative direction. And then it will, actually, let me draw that a little better. I don't like that either. So, and then at x equals 3, it's still going down, but now it switches concavity. And so it's going to go concave up until it gets to x equals 4. It's going to be a min, and then it's going to go up and to the right. And so this is a possible sketch of what that graph could look like, right? Because it's down and concave up, or decreasing and concave up, increasing and concave up, increasing concave down, decreasing concave down, decreasing concave up to increasing concave up. And here's a possibility for what that could be if we actually gave it values. And so the points to keep in mind were x equals 1 or 0, 1, 2, 3, and 4. That's where all the important stuff happened. We had a local min, an inflection point, a local max, an inflection point, and a local min. And so they don't have to be exactly the same. It just has to be kind of similar, but it follows the same kind of up and downs that they did. And that's the basic idea, is that if you make these number lines for f prime and f double prime, then you have everything you really need, sans maybe what the actual values are at the relative max and min, but you have mostly everything you need to graph. And so let's do an example. So let's use the graphing guidelines to graph this. The first thing we're going to do is we're going to find what the derivative are. The derivative is going to be x squared minus 400, and f double prime of x is going to be 2x. And then we're going to make number lines for those two guys. So here's the number line for f prime of x. So here's the f prime of x number line, and then we'll make an f double prime of x number line. Maybe right here to right here. And so the values that we're going to put for the f prime of x number line, we're going to do the critical values. And so if x squared equals 400, so if we set this equal to 0 and set that equal to 0, then x equals, what is it, plus or minus square root of 400, which is 20, I believe. So plus or minus 20. And then x equals 0 is going to be our critical point here. So maybe I'll put negative 20 here. I'll put 20 there, and then I'll put 0 right here. And now I want to test. If I plug in a number into here less than negative 20, so for instance, negative 30. So let's do negative 30 as our test point. F prime of negative 30 is going to be positive or negative. It's going to be positive, right? Because this number will be bigger than minus 400. And so this is going to be plus. So maybe I'll do this in red. So plus, plus, plus. And then it's 0 right here. And then let's do 0. Let's do 0 as our test point. F prime of 0, that's going to be less than, that's going to be negative. And so it's negative, negative, negative. And then f prime of something bigger, for instance, 30, that will also be positive. And so it'll be positive, positive, positive. So it's going to go up, it's going to go down, and it's going to go up, something like that. And then now we can do the concavity. Concavity is really easy. F double prime of negative 1 is less than 0 because it's just 2x, right? So that's negative. So it's concave down here. And then f double prime of 1 is bigger than 0, so it's positive here. So it's concave up. And so now we really have all the information we need to graph this guy. The final thing I would do is I would find what the values are, what the function values are at those 3 important points, and those will kind of be our anchor points. So let's find values of f of x at x equals negative 20, 0, and 20, because those are kind of our anchor points, right? Because that's the relative max, the relative min. So this is the max, this is the min, and then this is the inflection point. Inflection point. And so those are going to be our kind of anchors for making the graph. And so let's find these values. So what is f of 20? You plug in 20 into here, and you get 20 cubed over 3 minus 400 times 20. Oh, I have no idea what that is. Let's see. So it's going to be 400, it's going to be 20 times 400 over 3 minus 400. So it's going to be a big negative number. It'll be 800 thirds. So it's 1600 thirds. 16,000 thirds, maybe? Let me just plug into a calculator. Again, if this was on an exam, I would just pick easier numbers so that you don't have to have this issue. But 20 times 20 times 20 divided by 3 times 2. So it's 16,000 divided by 3 negative. So 16,000 divided by 3. I believe that is right. It will be 800 times 20. Yep, over 3. So this is roughly 5,000, negative 5,333.33. And then f of 0, that one's easy, thankfully. F of 0 is just 0. And then f of negative 20 is going to be very similar. It'll be negative 20 cubed over 3 minus 400 times negative 20, which that's going to be positive. So positive 20 cubed minus, and then times 3 over 3, and then minus 20 cubed over 3. And so this is going to give us positive 5,333.33. And so that will be, those will be the kind of anchor points for our function. And so at negative 20, the function value is positive 5,333. So this is the point negative 20 comma 5,333.3. And then at 0, it's 0. And then at positive 20, we'll have that point, it's 20 comma 5,000, negative 5,333.3. And so the function will look something like this. So it's increasing, and then it hits there, and it's decreasing till it goes through the middle. Then it changes, changes inflection until it rounds out there, and then it comes back up like that. You could also find where the zeros of this function are to find where that point is and that point is. And the way you would do that is you just set the function, this function equal to 0, and see when it's 0. And so we could do that to find what the actual values are, but that's not super necessary. And so this would be our graph, and it satisfies all the things that our number line said. It tells us when it's increasing from negative infinity to negative 20, and from 20 to infinity. And it's decreasing from negative 20 to 20, has an inflection point at 0 because it's concave down here and concave up there. And so that's how we use the graphing guidelines to give us a really good sketch of this graph without having to do a whole lot of work. And now if we saw a computer generated thing, we'd understand that, okay, that makes sense. Okay, let's do another one using some trig functions. So again, what we're going to do is we're going to find the critical points and the possible inflection points. So the derivative is going to be 1 and then minus 2 sine x. And then the second derivative, we set that equal to 0. And so that means that sine of x is equal to 1/2. And so when is sine of x equal to 1 at 1/2? What angle? And it's between 0 and pi over 2. So if you drew like a little unit circle, where's the y value between 0 and pi? What angle is the y value 1/2? And it's right here. Oh, excuse me. And here. So it's at those two angles. That's when the y value is 1/2. And those angles are pi over 6 and 5 pi over 6. And then f double prime of x would be -2 cosine of x. And we want to set that equal to 0. And so when is cosine of x 0? It's at pi over 2. That's when it, and so x equals pi over 2. So those are going to be our kind of points. So let's make our number lines. Here's our f prime of x number line, our f double prime of x number line. So in f prime of x, we're going to put the endpoints. We might as well put the endpoints in there to have an idea, because we know it's stopping there. And then we're going to put the critical points, which is pi over 6, and then 5 pi over 6. 5 pi over 6. That's where the derivative is 0. The derivative is 0 there and there. And then if we plug in a test point here, and we plug it into the derivative, whoops. The way we can kind of think about this, if I plug in an angle smaller than pi over 6, then this will be less than 1/2, right? That will be smaller than 1/2. The y value will be smaller than 1/2. So 1 minus something smaller than 1/2 will mean that this will be positive. And so this is going to be positive. So f prime of, for instance, pi, you could also just, I guess, do 0. So we could use 0 as our test point. So f prime of 0, because it's on this side of it, and so that will work. And f prime of 0 is positive, and so that works. To do one on the middle, let's do f prime of pi over 2. If you plug in pi over 2, sine is 1, and so this whole thing will be negative, and so this is less than 0, and so it'll go down like that. And we can plug in pi over here on this side. F prime of pi, if you plug in pi, it's also going to be 0 for sine, and so it'll be positive. So that's what the sine chart will look like here. Positive, negative, positive. So this is going to be a relative max, and this one's going to be a relative min. Let me move this up here. So this is the max, this is the min. And now let's go to our critical point. So, whoops. Let's make this in black. So here's 0, and then pi over 2 is probably right here. Then pi. So this is where the inflection point will be. If you do f double prime of 0, for instance, if you plug in 0 into this, that will be negative. And so it's negative concavity, which makes sense because there's a max there. And then if you test it over here with, say, for instance, f double prime of pi, that will be positive because it will be -1, and -1 times -2 is positive. And so it's concave up. And so that's what it looks like. And so now to kind of anchor our thing, we're going to plug in the values of the endpoint, the critical points, and the inflection point. And that's what these 5 calculations all are. And so you get 2.55, 1.57, 0.9, and 1.4. Just to save us some time, I already did those ahead of him. But all you do is you just plug them into the function. And if you do that, you get this kind of graph. So that's, let me zoom out a sec. So this is f of 0, 2. This is 2.55. This is 1.57. And then this is the low point of 0.9. And then this is the next point of 1.4. So this is the function. So this is f of x equals x plus 2 cosine x. And so it has a max there, has a min there, and inflection point there. And so it actually looks kind of similar to our last function, but that's the idea. And so we just make the number lines. And so this, again, is the key. Whoops. This is the key part, is knowing how to make this number line for the first derivative and second derivative. If you know that, and then you can plug in some values, then you have a real good shot of being able to graph these things. Let's do one last example. So use graphing guidelines to graph this guy. And x cannot be plus or minus 1 because that would make the bottom 0, right? So these are going to be our vertical asymptotes. And so let's take the derivative. The derivative here is going to be a little bit more difficult, but we can do it. Using the quotient rule, it's low, d high, which is going to be 30x squared, minus high, 10x cubed, d low, which is 2x. all over low squared, x squared minus 1 squared. That's the derivative, which if we simplify this, we're going to get 40x to the fourth minus 30x squared, and then minus 20x to the fourth all over x squared minus 1 squared. And then what does that simplify to? Well, we can pull out, if we pull out an x to the 4, so let me simplify this one more time. So what's this equal to? 20x to the fourth minus 30x squared. So let me just pull out the 10x squared. So 10x squared, and then on top would be 2x squared minus 3. That's on top. And then on bottom will be x squared minus 1 squared. And so the critical points are the things that make this 0. And so x equals 0, or x equals, if you add 3 and then solve, it'll be plus or minus the square root of 3/2. That's setting this one equal to 0. And so those are our critical points. And then, oh gosh, we have to do the second derivative of this guy. The second derivative of this guy is not going to be fun. Oh man, do I even want to do the second derivative of this guy? I guess I can. The second derivative of this guy is low d high. Okay. So actually I made a mistake here. So this should be 30x squared. And so this actually shouldn't be a 2. This should just be, this is just going to be a x squared minus 3. And so it's plus or minus root 3. Root 3. And then I'm going to cheat to find the second derivative because it is going to be a major pain in the butt and I don't want to do it. So I'm going to take it from the thing. I know that's cheating, but just for time, I don't really want to calculate this derivative because it's just going to be a pain in the butt. So when you have one on an exam, I'll make sure that the derivative is not nearly as hard as that. But that's what the second derivative is, which can be found using the quotient rule. It's not difficult, it's just more tedious than anything. And so let me find that. Where did it go? Cut. And we'll paste it right here. So that's what the second derivative is. And so what are the critical values for this? The critical values for that, let me make sure that I did the first derivative correctly. Yeah, the first derivative is correct. Okay. The critical values for this, so if that equals 0, so what are the possible inflection points? So x equals 0, or x squared plus 3 equals 0. So that never goes. And so it's really just going to be x equals 0, just this top one, just that one. And then the bottom at the asymptotes, that doesn't matter because it's the same as the asymptotes. So we don't count those points. All right, so now how do we use all this information? Let's first put in the asymptotes. So this is going to be -1, -1. And then let's do maybe 1 and 1. And then we have a possible inflection point at 0 and a possible critical point at 0. And then plus or minus root 3. So let's say that this is root 3 and this is negative root 3. And so we need to plug in some test points into there. So things to the left of negative root 3, if you plug in a number smaller than negative root 3, so for instance, f prime of -2, if you plug in -2, that will be positive. This will be bigger than that, so it's positive, positive. And then the bottom is always positive, right? Because the squared, so we don't have to worry about that. And so this is positive, 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 so it's positive. And then if we plug in something between these two values, then this thing will be smaller than that guy. So this guy will be negative. That one will still be positive. That's still positive. And so this is actually going to be negative, and it's 0 right here. So it's plus, minus, so this is a max. And then if we plug in a number here, if we plug in a number between -1 and 0, this is always positive. This is positive, and then this one will still be negative. And so it's going to be negative still. So it doesn't change, which makes sense because this is a vertical asymptote and that's a vertical asymptote, vertical asymptote, vertical asymptote. If we plug in a number over here on this side, this one will be positive. This one will still be negative, and that one will still be positive, and so it's still going to be negative. So plugging in a number there, it's still negative. Plugging in a number here, still negative. So it's still going to be decreasing. And if we plug in a number bigger than √3, this will be positive, that will be positive, and that's positive, and so we get a positive. And so this is 0, so decreasing, decreasing, increasing, so this is a min. And now we'll look at the concavity. If we do f double prime of -2, plugging in -2 into this, that will be negative. This is always going to be positive. And then this will actually change sign depending on what. But if you plug in -2 here, that's bigger than that. And so this will be positive. So positive, negative, positive would be negative. So it's negative concavity there. If we plug in something right here between -1 and 0, the concavity is actually going to change. This part will still be negative. This part will still be positive. But now the bottom, because we plug in a number between -1, that will be smaller than that. And so the bottom is negative. And so this will actually be positive. So for instance, f double prime of -0.5, that is greater than 0. This is less than 0. Doing that same argument again, you're going to see that this is actually negative. And so this is a concavity changer. And then if you plug in a number bigger than 1, that's positive, that's positive, that's positive. And so everything is positive. Also, the reason that this one is negative is because the bottom is negative and the tops are both positive. So f double prime of 0.5 greater than 0. F double prime of 2 is, oh, sorry, that should be less than 0. F double prime is less than 0, and f double prime of 2 is greater than 0. And so that's what it looks like. So it'll be concave down, concave up, concave down, concave up. And so these technically are not inflection points, not inflection points. The reason being is because these are not points of the function, right? Those are the asymptotes. And then to kind of anchor it, we'll get what the max value is. So when you plug in -√3, you get roughly -25.5. If you plug in 0, you get 0. And if you plug in √3, you get 25.5. And so this is what our function will look like. And so let's graph it. So if you plug in -√3, you get -25.5, which will be roughly about there. And then if you plug in 0, you get 0. And if you plug in positive √3, you get positive 25.5, which would be something like right about there. It is concave down on this whole part, and it's increasing from the right and then down and then decreasing. So it'll look something like that because that's an absolute, or it's a relative max. And then it's concave up here. So it's concave up, but decreasing. And then it changes concavity, but it's still decreasing. And so it looks something like that, right? Because it needs to be decreasing from -√3 to √3. It's always decreasing, but then it's concave up and concave down. It switches concavity. So it's going to look kind of like an x-cubed function. And then finally, we need to be decreasing, then increasing, and concave up on this last little bit. So decreasing, minimum, increasing. And so it looks something like that. And so that's what our function looks like. So this is our rational function. And that's a pretty good graph. So the things I'd be looking for is, do you know where the relative max and min are, where it's 0? Do you have the concavity correct? And so again, all the important stuff is in the first and second derivative test number line. And I promise I'll do a much easier rational function than that on an exam. All right, that should be everything you need. Good luck.